60 years.
It's easy to think that with the great leaps we've made in understanding and exploiting electricity, there's little left to learn about it. But we'd be wrong. For instance, making the circuits smaller and smaller meant that a particular feature of electricity that had been known about for over a century was becoming more and more problematic: resistance. A computer chip has to be continuously cooled. If you take away the fan, this is what happens. Wow, that's shooting up. 100, 120, 130 degrees. "200 degrees, and it cut out. That just took a few seconds and the chip is well and truly cooked. You see, as the electrons flow through the chip, they're not just traveling around unimpeded, they're bumping into the atoms of silicon. And the energy being lost by these electrons is producing heat. Now, sometimes this was useful. Inventors made electric heaters and ovens. And whenever they got something to glow white hot, well, that's a light bulb. But resistance in electronic apparatus and in power lines is the major waste of energy and a huge problem. It's thought that resistance wastes up to 20% of all the electricity we generate. It's one of the greatest problems of modern times. And the search is on for a way to solve the problem of resistance. What we think of as temperature is really a measure of how much the atoms in a material are vibrating. And if the atoms are vibrating, then electrons flowing through are more likely to bump into them. So in general, the hotter the material, the higher its electrical resistance. And the cooler it is, the lower the resistance. But what happens if you cool something right down, close to absolute zero, minus 273 degrees Celsius? Well, at absolute zero, there's no heat at all. And so the atoms aren't moving at all. What happens then to the flow of electricity, the flow of electrons? Using a special device called a cryostat that can keep things close to absolute zero, we can find out. Inside this cryostat, in this coil, is mercury, the famous liquid metal, and it forms part of an electric circuit. Now, this equipment here measures the resistance in the mercury. But look what happens as I lower the mercury into the coldest part of the cryostat. There it is. The resistance has dropped to absolutely nothing. Mercury, like many substances we now know, have this property. It's called becoming superconducting, which means they have no resistance at all to the flow of electricity. But these materials only work when they're very, very cold. If we could use a superconducting material in our power cables and in our electronic apparatus, we'd avoid losing so much of our precious electrical energy through resistance. The problem, of course, is that superconductors had to be kept at extremely low temperatures. Then, in 1986, a breakthrough was made.
In a small laboratory near Zurich, Switzerland, IBM physicists recently discovered superconductivity in a new class of materials that is being called one of the most important scientific breakthroughs in many decades.
This is a block of the same material made by the researchers in Switzerland. It doesn't look very remarkable, but if you cool it down with liquid nitrogen, something special happens. It becomes a superconductor. And because electricity and magnetism are so tightly linked, that gives it equally extraordinary magnetic properties. This magnet is suspended, levitating above the superconductor. The exciting thing is that although cold, this material is way above absolute zero. These magnetic fields are so strong that not only can they support the weight of this magnet, but they should also support my weight. I'm about to be levitated. Oh, it's a very, very strange sensation. When this material was first discovered in 1986, it created a revolution. Not only had no one considered that it might be superconducting, but it was doing so at a temperature much warmer than anyone had thought possible.
We are tantalizingly close to getting room temperature superconductors. We're not there yet, but one day a new material will be found. And when we put that into our electronics equipment, we could build a cheaper, better, more sustainable world.
Today, materials have been produced that exhibit this phenomenon at the sort of temperatures you get in your freezer. But these new superconductors can't be fully explained by the theoreticians. So without a complete understanding, experimentalists are often guided as much by luck as they are by a proper scientific understanding. Recently, a laboratory in Japan held a party in which they ended up dosing their superconductors with a range of alcoholic beverages. Unexpectedly, they found that red wine improves the performance of the superconductors. Electrical research now has the potential once again to revolutionize our world if room temperature superconductors can be found.